Next we have Kaustav Mitra, satellite kinematics, galaxies and halos, and more.
Hi, I'm Kaustav Mitra. I'm a graduate student at Yale University working with Frank Vandenbach, and I'll be talking using satellite kinematics to know more about galaxies, halos, and the universe as a whole. So I don't need to introduce galaxy-halo connection in this session. It's obviously the best the linking machinery to connect what we can see in the universe and what governs the dynamics and growth of structure in the universe. And it's crucial for our understanding of galaxy formation and evolution. It's critical for cosmology using large-scale structure of the universe. And for cosmology particularly, the commonly used probes are galaxy clustering and galaxy-galaxy lensing. But both of these probes, galaxy clustering and lensing, which are commonly used in cosmology, are plagued by something called the halo assembly bias, which is to say that clustering of halos not only depend on the halo mass, but can also depend on secondary halo properties, such as the left-hand side shows more concentrated halos, and they even visibly show higher clustering strength. So galaxy clustering can depend on secondary halo properties, and it's hard to model that, but it can cause systematic biases if not accounted for properly. Kinematics, however, on the other hand, is a very clean probe of halo potential well. It doesn't depend on halo clustering on larger scales, so it's unaffected by halo assembly bias. Now, Zwicky in 1933 used kinematics of galaxies in coma clusters to first hypothesize the existence of dunkle materie or dark matter. But it has been a widely underutilized probe, I would say. The basic concept of using kinematics to do galaxy-halo connection is just this. More massive halos should have faster moving satellites. So if we can characterize the motion of satellite galaxies, we should be able to constrain the halo potential well and thus the halo mass. Now, just using that simple prescription of kinematics, I'll try to answer 4 different questions in the next 10 minutes. First question, what is the nature of satellite galaxy orbits in a group of galaxies? Now, Barry has talked about velocity anisotropy, but that was for dark matter particles. Here, I'm asking the question, what is the velocity anisotropy of satellite galaxies themselves in the halo? So basically, what is the nature of their orbit? And does it agree with what we see in simulations? For question 2, obviously this plot has been shown by Sebastian, and he stressed on this, that this is a fantastic agreement between different techniques and probes of galaxy-halo connection. They all agree. But if we look at the scatter around this relationship, then, well, things get more complicated. So these are SAMs and hydrosins, but all of the top things are observations and empirical modeling of the scatter in the stellar mass of the central galaxy as a function of halo mass. And they are all over the place. Some studies conclude that there is a decreasing trend of scatter as you go to higher halo masses. Some studies do not show that. So can we probe this scatter very precisely, and can we reconcile the fact that some studies show the decreasing trend of scatter with halo mass? So I'll try to answer that question of scatter in galaxy-halo connection very precisely. Number 3. Subhalos in high-resolution dark matter simulations do not follow pure NFW. They seem to be slightly more extended. They seem to have kind of chord profile. It also depends on the simulation. What do satellites look like in the real universe? So what is the radial profile of satellite galaxies? Do they agree with pure NFW or that of the subhalos? And question 4, can we use galaxy-halo connection to do cosmology in this omega matter sigma 8 plane? And Daisuke talked about the S8 tension today morning. So this is basically the S8 tension, this discrepancy, not a very strong one, but consistent discrepancy between the low Z probes of large-scale structure, mostly using lensing, and high Z probes like CMB. Okay, so satellite kinematics has been traditionally done this way. You have a redshift survey of galaxies. You select primaries and secondaries based on some isolation criteria. You plot the line of sight velocity difference between the primaries and secondaries as a function of the primary galaxy luminosity. And just by looking at this, you can see that the velocity dispersion increases as you go to higher luminosity primaries, indicating higher luminosity primaries live in more massive halos. Now, to get the mass, what people usually do is bin this in luminosity of primary, and that roughly looks like a Gaussian distribution of velocities. So you get some sigma square, and from that you can use virial theorem to get some halo mass and do this for many luminosity bins and get the mass luminosity relation. You can do something more fancy with Jean's equation. There are ways to get the scatter around it as well. But this is the traditional approach, but it has many flaws that we can discuss later. One of the big things is that it has mass mixing in it, so you're basically combining primaries of same luminosity, but they can live in very different halo masses. So you're combining the kinematics of many different halo masses together and trying to get an estimate, and that can bias your results. What we do now is Bayesian hierarchical inference of satellite kinematics using something called Basilisk. We do not bin the data at all by luminosity or by anything else. What we try to do is we try to forward model the entire phase space distribution of all primaries and secondaries taken together. So you can go to individual primary secondary pair and ask what is the probability that it has this particular velocity and that particular projected separation, and for any given mass and given luminosity and given redshift, then you combine that with the galaxy halo connection parameterization that you have and marginalize over halo mass and combine this probability for all secondaries and all primaries. So this is an unbinned way to do the entire phase space modeling of the entire information that you get from the redshift survey. So most of my PhD work has been focused on drastically improving this methodology. The paper will be on arXiv in a few days, hopefully. We are waiting for the final green signal. I would like to highlight a few of the major improvements in satellite kinematics methodology that we have done. One is we forward modeling the majority of impurities, by which I mean satellites that get misidentified as primary. So in our primary secondary selection, there is always a misidentification. Satellites can get selected as primaries. Interlopers, which is background and foreground galaxies, can get selected as satellites. We do a forward modeling of all of that. We have drastically improved the interloper modeling, including dynamically coupled interlopers. And that's a very hard thing to do because you can't just do a background subtraction. Interlopers do show a peak and have a signature similar to that of satellites. We have introduced modeling of the satellite abundance as well, because otherwise you throw away, in a SDSS-like survey, you throw away 90% of the data because 90% of primaries do not have a spectroscopically detected segment. So those in traditional satellite kinematics is just thrown away, but that is a crucial information. And finally, we have extended our satellite kinematics modeling to fourth order moments of the velocity distribution and we model the full phase space distribution very accurately to break mass anisotropy degeneracy. And this is kind of showing that point. You can look at satellites with different projected separation, and we can very accurately predict what their line of sight velocity distribution should look like. So we model the full phase space distribution instead of using any summary set. Okay, so we have extensively tested our methodology on realistic mock data, and we can very accurately recover the main galaxy halo connection. Now this is central galaxy luminosity versus halo mass. Note that when we select primaries, we are biased high because we preferentially select more luminous primaries. However, we accurately reproduce the true underlying distribution. And this can be seen from the conditional luminosity function and halo occupation distribution as well. So I'll skip over these. I'll try to answer the questions that I introduced. So firstly, what is the nature of the satellite orbits? Turns out in SDSS, they are radially biased. And we have seen that it very well agrees with what we find in simulation. Secondly, about the scatter, we very precisely measured the scatter, and we model the replacement of central galaxies with brightest halo satellites, and we can show that this downward decreasing trend in previous work has been dominated by inclusion of brightest halo galaxy satellites as primary. About the distribution of satellite radial profile, we show that it's about 1.7 times the scale radius of the underlying dark matter distribution. So satellites are more extended, and we can reject NFW profile at greater than 5 sigma confidence. And finally, about the SA tension, what we do is we constrain galaxy halo connection over the entire omega matter sigmoid plane, and we see that it's extremely robust because satellite kinematics is very insensitive to the underlying cosmology. So it's extremely robust inference of galaxy halo connection. So then what we can do is we combine that galaxy halo connection with the halo mass function for different cosmologies to get the galaxy luminosity function. And the galaxy luminosity function will only fit the data best for the true underlying cosmology, and thus it gives us a handle on constraining cosmology. So we have tested it on mock data, and it recovers cosmology perfectly, and this is what we get in SDSS. It shows the SA tension very clearly without assembly bias. It's just luminosity function and satellite kinematics. However, if we include baryonic correction, and Josephine has talked about this on Friday, it shifts like this. And from that, what I conclude is that probably SA tension is a result of certain systematics that we haven't taken into account. If we take baryonic correction into account, we are perfectly consistent with plan. Thank you.
Thanks. Okay, can we have Yiming come on and get set up? One quick question maybe while he's setting up.
This is an easy one. Could you explain, looking at this diagram, how you conclude that there's no S8 tension when you take baryonic effects into account?
Well, it's perfectly consistent with, I mean, that's true. So I would have loved it were perfectly on the plan. That would be a fantastic result. It's very unfortunate that we are kind of in the middle of the two, and we are consistent with this as well as planned. So that's an unfortunate result, but Right. So what I was trying to say is, turns out taking baryonic effects into account in satellite kinematics very clearly indicates a shift in the cosmology, and that can be a relevant thing in other works as well. I mean, it's definitely more complicated than that, but people have taken into a baryonic correction. Some have come to the conclusion that there is no tension, some still show tension with baryonic effects. So yeah, it's complicated, but we do not find any effect tension with baryonic effects.
Okay, thanks again.